Hello there. Welcome to Astraveo's continuing education series, where for our podcast listeners, we talk about mathematics, the physical sciences, of course the natural world, and our personal favourites, astronomy. Now, you know Joseph and I are all up in and about astronomy. We get super excited about that stuff. So let's get going. Hello, good evening, and welcome back to Astraveo's continuing education series. Now, this evening we're going to be talking about Kepler's laws of planetary motion. Now, this is a really interesting part of astronomy, solar system astronomy. And essentially it's a sort of historical leftover from the change from when the philosophers and scientists believed that everything orbited the Earth, a geocentric system, to where we were able to prove that everything in the solar system essentially orbits the sun, a heliocentric system. And so we're talking really about the time of Copernicus, the observations of Tycho Brahe, then leading into the work that Kepler did. And then Kepler, of course, naturally became part of the historical legacy of Newton, who was able to tie it all together with gravity. So essentially what Kepler was able to do was, just through looking at the sort of data, really, the observational data that Tycho Brahe had produced once Copernicus had come up with the idea of that the solar system motions could be explained by having the sun at the center of the system and not the Earth, which was, of course, a concept that had gone back thousands of years to the ancient Greeks. Really, Kepler was able to then quantify and understand the solar system mechanics as we know them today. In a very simplistic form, but he definitely had the right idea, and in fact, in detail, his theories still work out well today. So he came up with three principal laws of planetary motion, and we'll write them out first, and then we can maybe do a little bit of investigation. So the first one is a planet, squeaky pen, orbits the sun in an ellipse. We'll talk about that in a second. An ellipse with the sun at one of the foci. Now, actually, let's do them one by one, because of course some of the statement is quite complex. We've got a few things to work out here. Well, first of all, what is an ellipse? Well, an ellipse really is just, very squeaky pen. It's just an ellipse is sort of like an oval. It's sort of like a squidgy circle. Now, a circle is also an ellipse. It's a perfect ellipse. It's perfectly circular. Has no eccentricity, no sort of squishiness. So this oval here that looks somewhat like an egg, that is an ellipse. Now, it has a couple of very nice mathematical properties here. This is called, as you might be able to guess, this is the whole way across. This is called the major axis, because of course it's the longest one, because don't forget this is squished. And as you might be able to tell, excuse me, this one is called the minor axis. Now, in a circle, a perfect circle, which I'm not sure I'm going to be able to draw, well, almost, with a very squeaky pen there. This time, squeaky pen syndrome has come back. This is pretty decent. I've got a little bit of a blip at the front here, at the top. There isn't really a semi-major and semi-minor axis, because these diameters are the same length. It's a perfect circle, if I could draw correctly. An ellipse says that you don't have to have a perfect circle. Okay. Although a circle is a special type of ellipse. It's almost like saying a square is a perfect rectangle. A rectangle normally is quadrilateral with two sets of parallel sides of different length, but the perfect rectangle is a square. Two sets of parallel lines of equal length. So a perfect ellipse is a circle. Other types of ellipses are sort of like a squidged circle, almost like an egg shape, a squidged oval. And so, in fact, almost everything in the solar system orbits the sun in an ellipse. Earth is pretty close. We are pretty close to being a perfect circle around our orbit around the sun, but it's not. It is slightly elliptical. Okay, the rest of this is also a little bit interesting. I've used this interesting term that we don't see in everyday life here, a foci or foci. What are foci? Well, foci is the plural of the word focus. One focus, two foci. Now, what happens when you get orbital mechanics, which is what Kepler essentially discovered? He was sort of the father of orbital mechanics, celestial mechanics for the solar system. In an ellipse like this, depending on the exact mass of the objects, you can have two focus points, two foci. Here's one, here's the other. So this is vastly exaggerated, especially for the Earth. But what essentially he's saying is, here's an ellipse, there's the sun, there's the other focus point. There's nothing there. It's just because the sun is at one focus. There's nothing but the other foci. An ellipse has two foci. And this would be a planet orbiting. A planet orbits the sun in an ellipse with the sun, with the sun at one of the focus points. Okay, so that's Kepler's first law. Planets orbit the sun in an ellipse where the sun sits at one of the focus points of that ellipse. That's all it is. Okay, so that's not too bad. Not too bad at all. That's a nice one. Okay, now the second one is a little bit interesting. It's actually amazing when you think about it that Kepler was able to work this out just from data tables of observations produced a little bit by Copernicus, but mostly Tycho Brahe. Just incredible. What he said was Kepler's law number 2. A line, and I'm sort of remembering this from my when I used to teach solar system physics back at Vanderbilt University and the University of Hawaii. I'm paraphrasing. If you look up the exact Kepler's laws, there are different ways of phrasing it, but the way I'm phrasing it here, the concepts are still valid. A line, now it's going to be an imaginary line, obviously, connecting a planet, a planet with the sun, sweeps out, and I'll explain this in a second, equal area in equal time. Now that is an interesting concept. An imaginary line connecting a planet with the sun as the planet moves in an elliptical orbit around the sun sweeps out equal area in equal time. Philosophically, it's amazing that Kepler was able to come up with this, but it has sort of real-world implications. And as usual, we'll draw ourselves a diagram. Now, I love purple, but somebody told me that purple's not the best. Well, that's not the world's worst ellipse. All right, I'm gonna go over it again with maybe the black pen, just so it really shows up. I really like purple, as you can probably tell from my shirt. It could probably be that bad guy in what's it called, Unbreakable, where Samuel L. Jackson plays the baddie. I love that purple. He always wore purple clothes. Super cool. Okay, so let's give ourselves the sun. And I'm going to put the sun just a little bit closer to the center of the very center of the ellipse. Now again, let's say we have a planet. I'm just going to put the planet here. So an imaginary line connecting the planet with the sun. There it is, squeaky pen. That imaginary line is going to sweep out equal areas in equal time. Well, what that means is, if this planet is moving, let's say it moves from there to there, we drew another imaginary line. Do you think it's going quickly here or more slowly? It's not entirely obvious, is it yet? I'll show you how we can figure that out. Well, the way it's written is this area here has to be the same somewhere else if the area swept out is in equal time. Well, let's say the planet is now orbited all the way around. P, and it's going, there's the planet, whoops. and it's going here. Now I'm going to give this a label, AB. Oh, that's just the planet, CD. What Kepler's law, second law, states is that if the time between A and B, the planet's orbiting, don't forget, if the time between A and B is the same as the time taken, I'm going to get rid of the P because that's just confusing, between C and D, if C and D is the same time as the time from A to B, these areas have to be the same. Equal time, equal time, equal areas. Now that's the sort of nice version. Let's take something like a comet. Okay, so these areas, I'm going to hash them, have to be the same if A to B and C to D are equal. Let us redo this, but let's make it a really long period comet. There's the sun. So if it's long period, it's going to be a long period comet with, this is very eccentric. You see how it's squidged? It's not like a perfect circle, which is a circle, which is a perfect ellipse. Now, what we call the eccentricity is high, so it's actually very squished down, almost like a very, very flattened egg. Now, this is quite a big area. Let's say here, the comet, okay, let's go this way this time. Well, we should, no, let's stay the same, because most objects in the solar system orbit the same way. If you remember, one of our series episodes was about planetary alignment and how all the planets in the solar system formed on the same plane because they came out of the same accretion disk. What that means is most objects in the solar system orbit and move in the same way, same direction. That's really important. It's one of the consequences of having the solar system objects formed out of the same accretion material, same accretion disk. So this comet is going this way. Now, we know, let's take Halley's Comet for instance. Halley's Comet, let's write this down. Halley's Comet, which I saw in 1986, I was 16, so I'm aging myself a little bit. Halley's Comet, the orbital period of Halley's Comet is 76 years. 76 years. So if it starts here, for instance, it takes 76 years to do this huge loop. And I saw it in 1986. So the next time it's going to be visible is, oh my gosh, I'm not even sure I can work that out in my head, 2072. So the odds on me seeing it are pretty low, but my children should see it, which is nice. So if the whole thing here takes 76 years, the part where it goes around the sun here, it wasn't visible in the sky for that long. A couple of months maybe, I can't remember, it was a long time ago, but it was a couple of months-ish. So if it spends a couple of months here, it's got about 75 years to do the rest of it. Now, even though it goes quite far out, it must mean that objects way out here, or this part of the orbit, are moving very, very slowly. So, I bet it's going to look something like this. If the time taken, and I'm sort of exaggerating here, it's actually going to be a lot less. If the time taken to go from here is time t, if that is also time t to go from there to there, these areas must be the same. And that is one of the consequences of Kepler's law. Imaginary lines connecting a planet sweep out equal areas in equal time. If the time it takes to orbit this segment is time t, and that is also time t, the area swept out is the same. And the natural consequence I was talking about is that when planetary objects, or in this case I used a comet, Halley's Comet, comets also follow follow Kepler's laws on planetary objects because they're just orbiting the sun. It is a planetary-like object, it's just a lot less massive. When it's in highly elliptical orbits, at the very far part of their orbit, they're moving very, very slowly in their orbits. And when they become closer to the sun, the closest to the sun, they become This is perihelion. Perihelion, they're moving very, very quickly. And so, in fact, you've seen this. In fact, I think when we did the the coronal mass ejection video in the Astraveo series, you saw some of these comets whizzing around. You could see them from the SOHO satellite. When they become very close to the sun in highly elliptical orbits, this is super quick. So they're orbiting very, very quickly here. And then they slow down, they slow down, they slow down. They're really slow here, and then they start speeding up again here. So this is a natural consequence of the orbital motions of planets and planet-like objects in the solar system. Okay, so it's very nice. Okay, now Kepler's third law is a nice one. I like Kepler's third law. Now, these are fundamental laws of the planets, and they're shown to be true even to this day, even though Kepler came up with them, 450 years ago-ish. I think Kepler died in 1632. I think he died in the same year that Isaac Newton was born. Oh, you think I'd know that? I can't remember, but I think it's 1632. Don't quote me. We can check it out after the video. If I get it wrong, put it in the comments and say, hey, you're in astronomy, you're supposed to know this stuff. I think it's 1632. I bet I'm plus or minus a year on that one, but anyway. Okay, Kepler's third law. This is a nice one. Kepler's third law states that let me just make sure I get this right. I'm going to have to think it through in my head first. It is A cubed is proportional to P squared. Let me just make sure I get that right. Yes. The square of the orbital. Okay, I don't need that anymore because I've got that right. Orbital period of a planet orbiting the sun is directly, I'm still thinking about the birth date of Sir Isaac Newton now, is directly proportional to the cube of its semi-major axis. Okay, now this is a big one to break down. Now we did talk about the major axis, but of course you would have a semi-major axis. It's just half of it, like a diameter and a radius. And what that really is stating is, again, let's give ourselves an ellipse. Oh, that's not too bad. That's the sun at one of the foci. That's going to be the minor axis. That's the major axis. So this is going to be the semi-major axis. With a planet, P, orbiting. Now let's say, for instance, the orbital, well, I've used P. You know what, I'm going to write the word planet, because I need P for something else. Planet. I'm going to say let P equal the period of orbital rotation. I can't spell rotation, it turns out. Let's try that one again, shall we? Orbital rotation. Nice. We know the semi-major axis. It's normally written, by the way, as the letter A. The semi-minor axis, as you might imagine, is written as B. That's just the mathematical norm. It's just how we, the original mathematicians that described this and wrote it down in journals, they use this construct. Sometimes we use X, Y, Z, sometimes alpha, beta, gamma, theta. Sometimes we use ABC. Mathematicians, they vary depending on what branch of mathematics and physics they're specialists in. When ellipticity and the theory of circles was developed, A's and B's. Okay, it's probably Euclidean actually. So semi-major axis A. Major axis. Okay, well, what Kepler's third law states that the square of the orbital period, P squared, of a planet orbiting is directly proportional. Right? So it's like the alpha symbol. We in a previous episode we did radiation and alpha particles. Well, it's not my world's best alpha. I'm going to do that again. Oops. There you go. It's like a Greek A. It's directly proportional to the cube of the semi-major axis. Okay. So it doesn't matter whether this is for Mars or Jupiter or Saturn or the asteroids in the asteroid belt. Comets also, again, a comet is just like a planetary object orbiting the sun, just it's highly elliptical and the mass is much lower. The square of its period is proportional to the cube of the semi-major axis. Empirically means with data, that turns out to be true for most of the objects in the solar system. Okay, now this symbol here, proportional to, is not the same as equals. It's a funny thing in mathematics. It can equal to it, but you have to have something called a constant of proportionality. It normally needs a fudge factor. And that fudge factor you can think of as a 0 point. It's just making sure the scales are the same. So you could have that p squared equals a cubed, but it wouldn't be exactly equal. It could be times 10 or times 3 or times 4.2 or 2 pi or something like that. In general, the square of the period, orbital period of a planet, is directly proportional to the cube of its semi-major axis, which means longer period planets, those that take longer to orbit the sun, must have greater semi-major axes. Now that makes sense, right? Because the Earth orbits the sun this is true, by the way, when the period is measured in years and the semi-major axis is measured in AU. An astronomical unit is the average distance from the Earth to the sun in its orbit. The Earth takes 1 year, Earth year of course, to orbit the sun. Its mean distance, its semi-major axis, is 1 AU. It's almost a formal definition, actually. Well, as we go out to Mars, I can't remember what Mars's exact orbital distance is, semi-major axis is. I think it's 1.6 AU. Well, 1.6 is greater than 1, and it's cubed, which must mean its orbital period is bigger. A bigger period means a small, slowly orbiting object around the sun. So Mars's orbital period is about 2 years, Earth years. So we're 1 year, Mars is 2, because it's farther out. Jupiter is farther out still. The semi-major axis of Jupiter is, oh my gosh, now you're asking me for my fundamental astronomy knowledge here. I think the semi-major axis of Jupiter is about 5.2 AU. Again, if I've got that number wrong, it's about 5. I think it's 5.2. If I get it wrong, put it in the comments and we'll correct it afterwards. It's good that we do our own research, right? But its orbital period is knocking on the door of 12 years. It's like 11.9 years. 11.86 years, I think. My memory's not quite what it was. I'm not a young chap anymore. I think it's 11.86 years. So as the orbital distance increases, so does the period. Its orbital period is slower. Now we know that because the outer planets, the gas giants, orbit more slowly. But that's a natural consequence of Kepler's third law because they're farther away from the sun. It makes perfect sense, actually. Now I'm going to leave this up because I really, you know me, I like a bit of mathematics. And I think, again, my friend Jasper in Hawaii, I can hear his little cogs thinking, turning. He's a very clever boy. I think he's saying to himself, well, David, whoops, I forgot just to raise my squared. You told me that this proportionality sign can make it be an equal sign, but it has to have a constant of proportionality. What is that? Well, we can figure it out. It's not too difficult. We need Newton. Newton, of course, came after Kepler. Well, as I said, I think their birthday and death date are the same, 1632-ish, plus or minus a year. We need to turn that into an equal sign, but we need a mathematical construct to do that, and we can do it. I'm going to make this circular just to make it easy. Life's easy with perfect circles. This is the sun. It doesn't matter which planet. It's not a great circle. This is clearly longer than this, so this is not a good circle. Let me try again because, Jasper, I know you're looking at me. You're a much better artist than me. You probably get that from your mother. She's a great artist. All right, well, it's close enough. It's close enough. So the semi-major axis is, I'm going to call this R because that's, for a perfect circle, we know R is radius, right? That's about normal. I'm going to give the sun a mass m, and I'm going to give the planet a little m, and it's orbiting with a period of, let's say, I don't know, t. Could be in years. Actually, it doesn't matter what the units are. I'm going to leave the units. It's orbiting with a period t. Actually, you know what? That is disingenuous. Let's call the period p, because, well, in that case, if I do that, I have to make sure. Well, no, I'm going to leave that as r. I'm going to leave that as r, and you'll see why in a second. Well, there are a couple of forces at play here. One of the forces is this planet is orbiting the sun. Now, it's orbiting the sun because of gravity. So we need to work out what is the force of gravity keeping that planet in orbit around the sun. Well, from Newton said the force of gravity is the universal gravitational constant times, the big mass, the small mass, divided by r squared. Big mass, small mass, divided by the distance squared. This is called an inverse square law. It's inversely proportional, the force is inversely proportional to the square of the distance. What that means is the gravitational force drops off by a factor of 4 when you double the distance. Which is why gravity at a distance doesn't work that well, because it drops off, the force drops off by a factor of 4 every time you double the distance. Okay, so this is a generalized expression for the gravitational force that the sun exerts on that planet. It does it on Earth as well, by the way, thank goodness. We're kept in the orbit. However, if you remember Newton's third law, action and reaction are equal and opposite. The gravitational force from the sun is attracting that planet. Well, the planet must have an equal reaction inward. So it's actually it's the other way around. That way. The gravitational force is making the planet pull toward the sun. Of course, it's in orbit, so it doesn't fall into the sun. It keeps moving. Well, there is a reactionary force here. Action and reaction are equal and opposite. Newton's third law. Well, this is a reaction to the centripetal force. And we can think of it as m, r. Now this, I've got a little omega here. So here's the mass, here's the r. Omega is the orbital velocity. How does that help us? This omega is a velocity, it's an angular velocity actually. I put orbital, It's an angular velocity. It's sweeping out an angle per unit time. Well, what we can do is we can equate these two because they must be equal and opposite, as Newton told us, Newton's third law. The gravitational attraction between the sun and the planet must equal the reaction to that, which is the force due to the orbital motion, the reaction to the centripetal force. Reaction to the centrifugal force. So, mr omega squared must equal the gravitational force between the two, which is g, which is just a constant, it's just a very big number, 6.67 times 10 to the minus 11. Mass of the sun, mass of the planet, over the orbital distance r squared. Now, this angular velocity, it's not easy to deal with in this system. However, we know something about it. There are 2 pi degrees, 2 pi in radians is 360 degrees, all the way around an ellipse or a circle is 360. So there's the angular part, and it does it in a given period, p. So there's the orbital angular velocity. It's 2 pi radians divided by the period of rotation in the orbit. So this omega really is 2 pi over p, the orbital period. So we have the mass of the planet. This is the small m, by the way, because it's here. mr omega squared. This equals omega, by the way, omega. So 2 pi over orbital period squared equals g big M small m over r squared. I think we're getting there. Well, let's get rid of the mass of the planet. Sort of doesn't matter, actually. Even for Jupiter, it's not that big of an effect. It's a 1% effect. For Earth, it's tiny. It's sort of like a decimal point. It's just not worth even considering because the mass of the sun is so much greater. So we have, whoops, I'm going to stay with black pen for a second. So we have r, 2 pi squared is 4 pi squared over p, all squared, don't forget, so that's squared, equals the gravitational constant, mass of the sun, over r squared. All right, well, now I do need some space, so I'm going to get rid of this. Actually, you know what? I'm going to put that part back, because we need it. Or maybe I'll put it over here. P squared is proportional to a cubed. Okay, so this is a really nice expression here. Here's an r squared, which is like an a squared, right? This is the semi-major axis, perfect circle, it's r. So r squared, I'm going to times both sides by r squared. Again, you know me and my mathematics. If there's an equal sign, what you do to one side, you have to do to another. The r squared cancel. R squared times r is r cubed. Let's just leave it like that for now. So 4 pi squared over p squared times r cubed equals gm, but the r's gone away. Gm. Let's times both sides by p squared. Times by p squared, equal sign. Whatever you do to one side, you do to the other. P squared. They cancel. You're left with 4 pi squared r cubed equals gm p squared. I'm now going to divide both sides by 4 pi squared, 4 pi squared. These cancel. You're left with r cubed equals gm over 4 pi squared p squared. Let me just make sure my mathematics is correct there. Okay, 2 pi squared over p. The m's go away. 4 pi squared over p squared. P squared goes up. R squared comes over here. R cubed 4 pi squared. R cubed 4 pi squared. It's gm p squared 4 pi. Yeah. Okay. So now we have it. We have our constant of proportionality. R cubed is like semi-major axis cubed. P squared, there's our p squared. But now we've turned a proportionality into an equal sign. So our constant of proportionality is gm over 4 pi squared. G is a constant, the gravitational constant, and m is the mass of the sun. So this is just a number. This number is known. This number is known. That's just some really big number. This is like 10 to the 30, 10 to the minus 11. You know, you're talking like 10 to the power 20-ish, maybe 10 to the power 19, divided by some number here. You know, it's about 10 to the power 19. A big, big number. But now we can plug in real numbers. If you can measure the orbital period of a planet in years, with this number, you can work out how far away from the sun it is. So now we can do fundamental astrophysics just from Kepler's third law, which he wrote 450 years ago, just by transposing and doing the celestial mechanics of the early work of Copernicus and Tycho Brahe. Amazing, amazing. Now, I know what you're saying in your head. Hang on, this is a perfect circle. Yes, we're going to need a tiny bit of extra mathematics in here to take into account eccentricity, how squished the orbit is. But for something like the Earth, a planet like the Earth, it's actually quite simple because the eccentricity is really, really low. We're pretty close to a circular orbit. So we can work out, if we know, say, we can measure our orbital period around the sun really quite easily, as long as we're able to work out the mass of the sun, and we can talk about that in another series, you can work out how far away from the sun we are. And that's how we work out some of these fundamental numbers in the solar system. Kepler's third law and Newton's law of gravitation allows you to stepwise through the fundamentals of astrophysics and observational astronomy, just by measurements, measuring orbital periods. It's really nice. Okay, there's Kepler's third law for you. 3 laws, I apologize. All right, thank you for watching. It was good fun. Thanks.